So we're beginning in week 12 here. We're close to the end of the course. Just three more lectures, including this one. So essentially, we're going to be finishing up inverse trig, and then we're going to find the area of a triangle using trig. So we left off, I think, on this slide. So to summarize, the domain and range of the inverse trigonometric functions are here. So the inverse, remember the domain and the range. So this is essentially the domain of the inverse of cos, -1 to 1, and the range goes from 0 to pi, and so on. And you can, of course, read this. So let's look at an example. So what angle does this line in the XY plane make with the positive x-axis? So we can draw a picture. Let's do a sketch and understand the question. So we have this line, y equals 3 divided by 7x. So we know it's going to go through the origin, and the slope is going to be 3 over 7. So this means, the rise is 3, and that run is 7. So that is our slope. So this is our line. So this point here will be 7, 3. So this means if we project this point down here, this is 3, and this is 7. Okay. So we're looking for this angle. And remember, this is 90 degrees here. And I'm just going to label our axis because it says the XY plane. So this is our x-axis, and this is our y-axis. So we made a triangle, and we can, of course, I'm just going to draw it again over here. So we have 3, we have 7, and our hypotenuse. Oops. So our angle here, our theta, well, opposite of it, directly opposite, let me write it down, is the 3, and adjacent is the 7. So we can find this angle clearly. So which trig function would we use? Yes? Right, perfect, tan. So we will use tan of theta is equal to, of course, and there's different ways to do this. Sine over cos. We know sine is opposite over the hypotenuse, and cos is adjacent over the hypotenuse. These cancel, and we get opposite over adjacent. So this, of course, implies our tan of our theta is equal to opposite 3 divided by adjacent 7. So then we, of course, use our calculators because we want the arctan or inverse tan, same thing, of 3/7. And we can compute this and get this arctan of 3/7 is approximately equal to, anyway, punching it in your calculator. Right, yep. 23.2 degrees. Your calculator should usually be in degrees. There was once a student who had their calculator in radians and didn't know the difference. So not be good. Okay, inverse trig identities. So in the previous section, we were talking about the inverse trig identity. So by virtue of these inverse functions, they satisfy like these following conditions. So the cos inverse of t, and then we take the cosine, is also equal to t for every t in between -1 and 1. And this is just a summary. Inverse, so sine inverse of t, and then take sine is also equal to t, for t being between -1 and 1. And tan inverse of t, and then take tan is also equal to t for every real number. So this is like where it kind of differs. So some examples where we have to be careful. Let's say we take cos of cos inverse of 1/2. Well, that's just going to be equal to 1/2 because this is in that domain. Sine of sine inverse of 0, well, this is going to be equal to 0 because 0 is between -1 and 1. Tan of tan inverse of 2 is equal to 2 because it's for every real number. So this is okay. Now, cos of cos inverse of 5, what is this equal to? What about the 5? No. And that's the trick, right? Because to go back to the definition, 5 would have to be between -1 and 1. And it's not between -1 and 1. 5 is outside. So, so it's not equal to 5 because 5 is not an element of -1 and 1. This symbol means not an element of, with a dash, not. And here's some more examples. Here's our definitions. So the inverse of cos of theta, taking cos is theta, where theta ranges from 0 to pi, and inverse of sine. So it's just being careful about what does theta equal here. So the inverse of sine of theta, taking sine, is equal to theta, for theta being an element, where it's equal to pi divided by 2 to pi divided by 2 in that set. And inverse of tan of theta, taking tan, is equal to theta, for theta being an element, where it's between -pi divided by 2 to pi divided by 2 And it doesn't include those brackets. If you remember those points, it goes up to infinity if you draw the graphs. So we could kind of, some examples of this are right over here is, let's say, cos of, so, And we could flip it the other way as well. So we could write it cos of, like, let's say, pi divided by 4. This is pi divided by 4. And sine inverse of sine of pi divided by 3 is equal to pi divided by 3, because this is also, these are in the domain of what theta can be in. So we have to note that the restrictions on the domain are necessary. And we could consider like this example. The cos of inverse of cos 2 pi, this actually does not equal 2 pi. Because you note that 2 pi is not in this range above of the composite of the cosine function with its inverse. So it can't be 2 pi. Because if you go back here, 2 pi is not in this range, as we can see. So instead, you have to like take more of a direct approach. So cos of 2 pi, well, if you plot the graph of this cos of 2 pi and you visualize it, this part here, this is the same as cos of 0. Well, cos of 0 is equal to 1. This is how we get this. So the cos inverse of 1 is equal to 0, which is not 2 pi. So therefore, we find the cos inverse of cos of 2 pi is actually equal to 0, which is not 2 pi. So it's kind of interesting, this little part here. I'll let you do this as an exercise. So, and I'll just make a little note to please try to see the restrictions. On the inverse trig function. Move forward. Now, suppose we had, as an example, the cos times 5 plus 1 is equal to this function, where the domain of this function is between this interval between 0 and pi. Find a formula for the inverse. It's kind of something like we did previously, like this. So you should be able to connect the dots and be able to do this. So what is the first step we do? So we have our function and we have f of x equals y. So we can rearrange this essentially, and we're solving for x. So it's exactly kind of what we did before. So y minus 1 is now equal to 5 cos of x. And then we divide by cos of x. So this implies y minus 1 divided by 5 is equal to cos of x. Okay, so we're trying to solve for x. So we want to apply cos inverse to both sides. So this implies, because whatever you do on the left, you do on the right. So we take that inverse of both sides. So we get cos inverse of y minus 1 divided by 5 equals x, because this is equal to cos inverse of cos of x. Same thing. So now if we wish, we could interchange x and y, and we get f of this inverse is equal to cos of inverse. And we're just flipping the x and y. So now this is an x minus 1 divided by 5. So that is our inverse. Okay. So it's like exactly what we did before. It just has a cos function. Give me a second. Okay, so what is the domain of the inverse of this function? So we first need to find the range of f. So let me make a little note here. So the range of f of x is equal to 1 plus 5 times cos of x. And we remember our domain here was 0 to pi, because that was what's given in the question here. So I'm just writing down it. So we're trying to find the range of this function first. So we could draw like a little sketch of just remembering what the cos of x cos is. Oops. So goes from 0 here to pi. Here's pi divided by 2. Okay. So the range of cos on 0 to pi is obviously going to be, goes from 1 to -1. So it's going to go from, the range is going to go from -1 to 1. Okay, so that's helpful. So then the range of 5 times cos of x is just going to be, we multiply it by 5. So it's going to be -1 times 5 times 1 times 5. So this is equal to -5 to 5. Then the range, when we add 1, so basically f of x 1 plus 5 cos of x, we're just adding 1, it's just going to be the same thing plus 1. So I'll just write it out, 1 plus -5, 1 plus 5. So this is equal to -4 and 6. So that is the range. Question asks you the domain of the inverse. So the domain is that range of f, if we remember. So the domain on f inverse is -4 to 6. So for part C, it says, find what is the range of the inverse of f? So we need to find the domain of f, but that was given in the question because we know the range of the inverse is going to be the domain of f. So I'll just make a little note. So the question gives us the domain of f is given in the question as 0 to pi. That's given. So if we recall, the range of f inverse is 0 to pi. So that's it. So sometimes we have to resort to drawing a right triangle to evaluate expressions involving inverse trig functions. So let's look at this. Evaluate cos sine inverse of 3/7. How do we do this? So we could say, and sometimes we let this part here equal to theta, where sine inverse of 3/7 is equal to theta. So then this becomes cos of theta. I'm just going to repeat it. So where theta is equal to sine inverse of 3/7. So if we have this, this means that if we take the inverse of both sides, we can take sine of theta is equal to 3/7. We should see that because we're just taking sine of both sides. This becomes 3/7. So this becomes sine of theta is equal to 3/7. Okay. So we're going to use this to help us solve. So the next step is we could draw a right angle triangle. This is our theta. And we have sine of 3/5. So that would be opposite, would be 3. This is opposite. And divided by our 7, our hypotenuse. Let me write that down. Sine of theta is equal to 3/7. So this is opposite. Divided by our hypotenuse. Again, remember, this is our opposite. This is our adjacent, our x side, our hypotenuse. And there are nice straight lines. Imagine. Okay. So we could find x. How do we find x? Anyone? How do we find x? So by our formula, our favorite formula, anyone? Okay. So we can just simply say 3 squared plus x squared is equal to 7 squared and solve. So this becomes 9 plus x squared equals 49. I'll quickly solve this. X becomes 40, or x squared becomes 40. Take that square root. So plus or minus square root of 40. This is obviously, we're going to take like the positive. We're going to say it's a distance, so it's not negative. So we can say it's this missing side has length square root of 40. Okay, so now if we remember, I'll just use another. This was our theta, and it's equal to cos of theta by definition. So we have our cos of theta is equal to adjacent over our hypotenuse. So that's x divided by 7. And we found what our x was, square root of 40 divided by 7. Because we're using the same right triangle. I'll just make a little note here. Okay, so cos of sine inverse of 3 over 7, we just found it, was therefore equal to square root of 40 divided by 7. So what we did was we substituted theta into that inner part of the function of the trig function. Now, here's another example where you could continue. Suppose t goes from -1 to 1 and it's not equal to 0. Find a formula for cos inverse of t of tan. So we're going to do that same idea, essentially, where we're going to take tan of cos inverse of t. And this part, of course, we're going to say that it's equal to our theta. and then we're going to kind of solve. So this implies our cos of inverse of t is equal to theta. So implies here cos of theta is equal to t. So this means down here, our tan of our angle, of course, remember, is sine over cos. So we're going to use this to kind of evaluate and find a formula for this. So this is just setting it up. Now, if we remember this pretty famous trig identity, cos squared plus sine squared is equal to 1, we can rearrange the previous question and it'll help us. So let me write this down. So remember, so we can take this and rearrange it for sine first. So sine squared of theta is equal to 1 minus cos squared of theta, which is also equal to theta, sine theta, equal plus or minus square root of 1 minus cos squared theta. Okay. Now from here, we said cos theta is equal to t, this part here. So if we remember this part, I'll write it down. Cos theta is equal to t from above. So this implies sine of our theta is equal to plus or minus square root of 1 minus t squared. So this means our tan of theta is equal to sine of theta over cos by definition. Our sine is what we just got here on the top. So this is plus or minus square root 1 minus t squared divided by cos, but cos is t. So it's equal to this. And we could just bring out the plus or minus in front if we wish. It's the same thing. 1 minus t squared, square root it, divided by t. So what did we just find? So we find that tan cos inverse of t here is equal to plus or minus square root 1 minus t squared divided by t. Wow. This is a t. So the stuff with trig in it is equal to actually something with no trig in it. The right side, this right side, there's no trig in it, but there's trig on the left hand side. So kind of shocking-ish. So here's some more formulas that I'm not sure how useful if they're the most useful formulas or not, But essentially, it says that we take like negative t, let's say, and take cos inverse of this. And this is equal to pi minus cos inverse of t. Negative t, and we take the inverse of that, of sine inverse of that, is equal to negative sine inverse of t. And when we have negative t, so there's a negative here, it's equal to, then we take the arctan of it, it's equal to negative arctan of t. So like there's these formulas. We can just kind of use these formulas to solve some questions. Not really sure how useful they are, but okay. So let's evaluate the following and apply those formulas. So let's say, so it's the same idea that we previously did in the other question. But this time we're going to say this inner part is equal to t. So this means the cos of inverse of t, where t is equal to, let's say, oh, there's a negative. Let's say, 1 second, putting a negative here. Let's not have it equal to the whole thing. Let's say t is equal to cos pi divided by 3. So this part, not the negative. So we're going to evaluate this where t is equal to cos pi divided by 3 or by 11 and apply the formula. So our cos inverse of negative t is equal to our pi, because let's go back. So there's a pi here. Pi minus cos of -1 of t. So our pi cos, and we have to do this because for the bounds. So make sure it's in. So cos inverse of cos pi divided by 11. So this is just equal to pi. Cos of pi over 11. Inverse is just pi divided by 11. So, and then we can compute this. So this is the same as 11 divided by 11 pi minus pi divided by 11. So this is just 10 pi divided by 11. So that helps us kind of solve that question. For this question, we do the same trick. This part is equal to t. So it means sine of inverse of negative t, where our t is equal to sine of pi divided by 5, or yeah. So we got negative, applying the formula, put a negative in front. Negative sine inverse of t. Okay. So then this is equal to negative sine inverse, and t is equal to this stuff. So this is just then pi divided by 5. Okay. So in the last one, same idea. This part, t is equal to tan pi divided by 7. So we're going to do tan inverse of negative t. And we have where our t here is equal to our tan, what I just said, pi divided by 7. So this means we bring it up front, so negative tan inverse of t, and then we can plug in our t again. So negative tan inverse of tan of pi divided by 7. This is just equal to negative pi divided by 7. Negative up here too. Sorry about that. I forgot about this negative in front. There's a negative right there. So the arc cosine and arc sine are related through this kind of nice identity. If we remember, cos inverse is the same as arc cos, and sine inverse is the same as arc sine. So we have like this nice kind of like identity here. So they relate to each other. Okay, so we could kind of use them, this identity, to solve like the and we could verify it. We can't actually really prove it. That will be a little bit too difficult. So let's verify this last identity for various values of t. So let's say when t equals to 0, what do we get? So cos of negative, so cos inverse of t when t is equal to 0. And we're going to verify so sine inverse of t, what happens of these values? So cos inverse of 0. So what number is equal to 0? So the cosine of what number is equal to 0? What would that be? Let's kind of draw it. So that would be pi divided by 2. And then we could do the same thing here. Sine inverse of 0, well, that's 0. Okay, so with these two combined, so cos inverse of 0 plus sine inverse of 0, we can see pi divided by 2 plus 0. So this is going to be pi divided by 2. Sorry. So this is what this identity says. When we add them, it's equal to pi divided by 2. Good. So for between t, between -1 and 1. So this works when t is equal to 0. What about when t is equal to 1/2? So we're just going to do the same logic. So cos inverse of 1/2, we can calculate this. So this would be pi divided by 3. This one's going to be pi divided by 6. So when we apply it to the formula or to the identity, we add these inverses. You see, get pi over 3 plus pi divided by 6. We add them, 2 pi divided by 6, common denominator. We get 3 pi divided by 6, which is the same as pi divided by 2. And the last one, t equals square root of 2 divided by 2. So let's, I'll just write it out. Cos inverse of square root of 2 divided by 2 is equal to, so the cos of basically what number is equal to square root of 2 divided by 2. Anyone? Also the sign. So what number is that? Right. Yep. And so pi divided by 4. So you could see, obviously, if we add these, just writing it out again, pi divided by 4 plus pi divided by 4, that's 2 pi divided by 4, which is pi divided by 2. Therefore, this property, this identity holds for like these t values between -1 and 1. So we just kind of like verified some examples. It's not a proof, but it helps. Us understand the identity. Recording. So we probably know this already, right? How to compute the area of a triangle. So we have essentially, let's say, so to compute like this area of a triangle, we know it's basically a half times the base times the height. And we could draw this, I hope. So let's say we have a nice triangle. This is our base, and our height is this point down. This is our height. Hope we know this. So we're going to extend, we're going to learn the basics, and then we're going to extend this. So let's draw a rectangle. And we'll see why like this is true. So if we draw a rectangle, and it has a height and it has a base. Now we could draw some triangles in our rectangle. Like here and here. So this will also have a height and the space. And you see like they're, let's say, 90 degrees everywhere in these corners. So let me color code it. You notice this area and this area, they're the same. And this area and this area, they're also the same. And we know the area of like a square or a rectangle is length times width. So this is like length times width. But we have half of it, so this makes sense. So it'd be half times base times height. So it's like we have basically two triangles in a rectangle. Okay, so let's find the area of a triangle that has sides of length 5 and 8, and this angle between those two sides. So step 1, draw our triangle. So I'm going to project down. So this is our length 5, and this is our base 8. Base is equal to 8. So we want to find the area. And between these two, we know the question also gives us the angle is 53 degrees. It's our theta. So what is our area? Question mark. And if I drew this nicely, this would be 90 degrees on both sides. Let me draw it a little nicer. A little misleading, my triangle. Okay. So let's find this value, this h here. So the sine of our angle, 53 degrees, is going to be opposite, which is, so opposite divided by our hypotenuse. So opposite is h, our height, divided by 5. So this implies our sine of 53 degrees is equal to h divided by 5. We just multiply. So h is equal to 5 times sine of 53 degrees. We can then use a calculator. So this would be, so use the calculator, I should say that. So 5 times, what is sine of 53 degrees? Yeah, like 0.8. So this is approximately equal to 4. Okay. So we have now, so if we use this calculator, we found sine of 53 degrees was approximately 0.4 or 8, sorry. So the area is going to be, well, area is a half times our base times our height. So it's approximately equal to a half. Our base is 8. And our height here is 4. So then it's 4 times 4, so 16. Okay. So what did we kind of see here? So that's straightforward, I would think. But let's see like a formula or something actually more interesting. So our height, what we found was our height here was equal to C. This is our value C times sine of that angle, theta. So we see area is, we can derive a formula for this. Area is equal to a half times the base times our C times that sine of that angle. So we just derive the formula. So our area, so if you have one side and you have the other side and you have the angle, you can drive it like using trig the long way, or you could see that it's a half times this base times this side times the sine of that angle. It's the same thing. It's just kind of interesting that you have a nice formula to derive it. So that example just showed that if we have this area of a triangle with sides B and C and an angle between them, let's just draw this, B and C. This angle. That the area is given by like this specific formula. So, but we have to make one little note. So note that it's between B and C. It's not this angle or this angle. It's the angle between those. So it's necessary that the angle or theta here is the one that is between those. Between the two sides. Huh. So we have a formula. Now, this can help us with different shapes as well. So let's look at this area, this parallelogram. It's hard for me to pronounce it. Sorry. But let's draw one. What is it first? So this side and this side, they are parallel, let's say, put a dash beside B. Maybe I'm not drawing it nicely. Oops, nope. Messing up again. There we go. Suppose they have the same, they're parallel and they have the same length. This side and this side, they are also parallel with side C. Okay, so we can draw triangles in them. And we notice here, this angle and this angle, they're the same. And this angle and this angle, they're the same. So the area here, what we just learned, this is going to be a half times B times C times our sine, or theta. And so is this area. So this is B times C times the sine of our angle. So we notice that therefore the area of the whole thing, so we see that, let me make a little note. So the area is so it's just going to be add those two areas together. So it's just going to be a half BC sine of theta plus a half BC sine of theta. We add them, a half plus a half times BC sine of theta. So this is just going to be BC sine of theta. So our area here is therefore BC sine of theta, which is what's given here. So the trick was basically drawing basically two triangles in this. So it's nice to know where like these formulas come from. Like it's essential to understand like the basics of, hey, like not, this is the formula, but where did that come from? So we took like, we just divide essentially this into two triangles and we get that. I think there's two ways to pronounce, so. Parallelogram or parallelogram. Not great at pronouncing words, sorry. So anyways, suppose, now when we take this, the side note here is that we take the arc sine, because the formula has a sine in it. So when we're taking the inverse of the sine function, relevant to the expression yields the smaller of the two angles between the two sides. And we're going to see this in an example. So let me draw this one again. So suppose we have, let me draw a sketch first. So we know the formula is area is equal BC times sine of theta. And our area here is 50. Our base here is 12. And our length here is 7. And our find the smaller angle between these sides, between 12 and 7. So find this angle. So this smaller angle, not this larger angle over here, because that would be bigger than the smaller one. So this is the smaller one. Because there's two angles. It doesn't matter which side is B and C, as long as this is the smaller angle. So then we just can apply this formula of 50 is equal to 12 times 7 times sine of theta. And we can compute this. So this is then 50 is equal to 84 sine of theta. So implies sine of theta is equal to 50 divided by 84. And then we take that inverse. So sine inverse of both sides. So then we get our theta is equal to sine inverse 50 divided by 84. And then we can compute this. So our angle is therefore, anyone? Right, perfect. 36.5 degrees. So then we found that angle. Just give me a second. So we're going to look at now polygons. So what is a polygon? So it's basically, so let me write a little note. Polygon, it's just a shape, so a geometric shape. Usually labeled by the number of sides. So for example, let's write an example here, like a hexagon. It's just a polynomial with 6 sides. So it's just, it depends basically on the number of sides you have. So it's just a polygon with 6 sides. And then Pentagon has 5 sides. So polygons are called regular. That just means that each side has the same length and all the interior angles are equal. The most obviously famous one would be the square. So the square is just a regular polygon. With 6 sides, or with, sorry, 4 sides. Why am I saying 6? So 4 sides. So that's straightforward. So find the area of an octagon. So an octagon has basically polygon with 8 sides. Okay. So what do we do? So find the area of this regular octagon with vertices are 8 equally spaced points on the unit circle. So we're going to draw that unit circle that we've done before. So let's draw it. It's really hard to draw nice circles. Okay. Just imagine. So this is our unit circle. Now we're going to divide it into 8 equal sides. So there's a point here, point here, point here, point here, and points on the axis. So we can divide it into kind of some kind of like pizza slices almost. And then it's flat here, it's flat here, it's flat here. These are straight lines. Straight lines. Sure, you can draw better than I can with this. Difficult for me. So this length here is 1, that's our B. These are all 1s. Because it's the unit circle. This side is, let's call it A, etc. So this is our regular octagon. So what is our area under this regular octagon? So we want to find the area under this. So it's not the area under the entire circle, it's the area under this octagon. So what is that? So the area of the regular octagon is what we're trying to calculate. So first we see that there's 8 equal triangles. So we have, you can count, but we have 8 triangles. So notice that first. So first, I'll just write a note to say that. We see that we have 8 equal triangles. Okay, so then it follows that so the angle between the whole thing is, so this angle here, if the whole thing is 360 degrees, one angle, what would one angle be? So the angle, the whole thing is 360 degrees, then divide by 8 would be just one of them. Or equivalently, 2 pi divided by 8 radians. So each angle, therefore, 360 divided by 8, and you can see just by like looking at the picture, what each one would be 45 degrees. Or equivalently, pi divided by 4 radians. Okay. So now we have some information. We can kind of put it all together and we can find the area. So using the formula previously that we kind of derived, we find that the area of each triangle is going to be, so the area is equal to a half. So the base here, so we have two sides, the base, and we have the other side. So we have B and we have C. So we know they're both equals 1 and 1 times that sine of that angle. So this would be a half times 1 times 1 times the sine of 45 degrees, which is equal to, if we calculate, approximately equal to, let's say a half times 1 times 1, sine of 45 is approximately, let's say 0.71. And we get our answer here is approximately equal to 0.355. However, that's for one triangle. We have 8 slices or pieces or whatever you want to say. So then therefore, then it's going to be 8 times our area. So this is the area for the given triangle or for the given rectangular octagon. So this is regular octagon. So therefore the area is going to be equal to 8 times 0.355, which is approximately equal to 2.84. So let's look at the face of a loony. So a loony is almost a regular 11-sided polygon. And the distance between the center of a loony to one of the vertices is about 1.3 centimeters. Find the area of the face of a loony. So let's try to draw like a little sketch of this Loony. I'll draw it's not easy again. So 1, 2, 3, 4, 5. Whoops. Maybe I'll try again. 2, 3, 4. Okay, that wasn't so great. So hard to draw. Really apologize. But you know what a Loony looks like. So 1, 2, this will be my last attempt. 3, 4, 5, 6, 7, 8, 9, 10. I'm gonna make these a little bit closer together. Imagine that's a Loony. Okay. So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11. I think you get the idea. Sorry, it's just, again, not easy. So this is a Loony, has 11 sides. Like this. And they all have like this distance A. And from the center to the vertice, it's 1.3 centimeters each one. If I drew it nicely, which I did not. So find the area of the face of the Loony is the question. So we assume that the Loony is a regular 11-sided polygon, and we split it into these 11-sided into 11 equal triangles. So that's what I tried to draw there. So essentially from the center to the vertex, there's 11 of these. So since each are of 11 triangles are the same, then we have like, do the same idea as we did before. We can find this angle essentially. So let me write some little notes down first. So since the Loony is assumed, to be a regular 11-sided polygon, we can split it into 11 equal triangles. So we do this by drawing the edges from the vertices of the Loony to the center. Okay. So like we did before, we can find that angle. And we have 11 basic triangles here. 2, 3, 4, 11, yeah. So since each of the 11 triangles are the same, suppose, they each have an angle of our theta, which is of course 360 degrees divided by 11. So this is also the same as 2 pi divided by 11 radians. Okay, so then the area of each triangle is just going to be equal to, well, we did this before. So the area is going to be a half. We know one side is 1.3. The other one is 1.3. So then, and then the sine of 360 degrees divided by 11, we can use a calculator. And we get a half times 1.3 squared times, calculate this value, calculator, which is 0.54. And our answer here for this part will be then 0.456. So, but now we have, that's one triangle. Now we have 11 of them. So you calculate that area times 11. So then the 11 times our area is the area of the Loony. So that's just simply, so the area will be of the Loony is just going to be 11, approximately 11 times 0.456, which is approximately 5.02 centimeters squared. Because it's centimeters times centimeters, so centimeters get squared, area is squared. So our last question. So each side of the Pentagon that houses the US Department of Defense has a length of 921 feet. So let's draw this. So this one's a little easier, I hope, to draw. So one side, 2 sides, 3 sides, 4 sides, 5 sides. So this I guess like these problems could appear in, you know, engineering, architecture. Has anyone wanted to be an architect ever? No? I thought about it once. But I clearly cannot draw with this. I'm actually a better artist than this. So this side of the Pentagon, so Pentagon has a regular, so it's just a regular polygon. with 5 sides. So we're going to split this. So this side is the same as this side, is the same as this side, same as this one, is the same as this one. So we want to find like these angles are all the same as well. So it's the same idea that we've previously done. F5. So we can split this pentagon into 5 equal sides. So 5 equal triangles. So we see, of course, so 5 times our theta is equal to 360 degrees. So our angle here is 360 degrees divided by 5, which is about 72 degrees, or 2/5 pi radians. Okay. So we could take one of these triangles. I'll write this on the next page. So let's take like this triangle. Next page. And redraw that specific triangle. Again, not my best triangles. Something like that. Okay. So this is 921. We found our angle was 72. This was 72 degrees. So this implies this little part, each part was, this is 36 degrees, and this is also 36 degrees. We have our height, we have our base. Okay. So now we can find, well, we don't know what our h is. So we know our tan of 36 degrees is equal our adjacent. This is our adjacent. So it's equal actually to opposite divided by adjacent. So our opposite here was over here. So it's equal to opposite. So opposite is 460.5. So just this part divided by our h. And this little part, if we wanted it in radians, is equal to tan of 5 divided by pi divided by 5 radians. Anyways, so the tan of 36 degrees is equal to 460.5 divided by h. So therefore h is equal to 460.5 divided by tan of 36 degrees. So this is approximately equal to 460.5, the tan of 36. Let's say we use a calculator, 0.73, which is approximately 630 feet. So then the area of this triangle, of this specific triangle, so our area is just half times 460, because we have our height now, or we have our base times our height. So 630, because we found that. We can compute this. And now that's one of them. But there was, if we go back, we see that's just this part of the triangle. There's 10 of them, so we multiply it by 10. Did anyone calculate this number? So then the area of the Pentagon is approximately 10 times this, which is I think 1450000 square feet.